Okay, next problem. So you're given 11.2 grams of oxygen, and you're asked to convert that to moles. Simple, right? We've done that before. We've done grams to moles before. Well, let's go through it. So 11.2. See if you notice the mistake. Grams of oxygen. Did you see it? Well, if you notice, oxygen is diatomic, which means that it appears in pairs in nature, which also means we're dealing with two oxygen. Now, if they wrote the problem like 11.2 grams of oxygen, then yeah, there's only one oxygen. They wrote down the atomic symbol, and we're only dealing with one oxygen. In the last problem, we dealt with 22 grams of CO2. And yeah, we're dealing with two oxygens because it has it right there. But when they write down just oxygen, we need to assume that there's two of them because in nature, or usually, oxygen appears in two. It's a diatomic element. And diatomic elements include oxygen, nitrogen, fluorine, hydrogen, iodine, bromine, and chlorine. So when they write down, say, this much of nitrogen, they don't just put the elemental symbol, they actually write down nitrogen. Then you could assume that you're working with two nitrogens. Just put a 2 next to all of these. All these elements are diatomic. They normally appear in pairs in nature, sometimes even more. So these elements are a little random, but I have a mnemonic device that helps me remember all of these. Ostriches never fly high in brown clouds. That's how I remember these elements. And if I write them down, if I write down just like the first letter or sometimes the first two letters for these last ones, I remember that it's oxygen, nitrogen, fluorine, hydrogen, iodine, bromine, chlorine. Ostriches never fly high in brown clouds. So we've got to remember those diatomic elements. You remember to treat them diatomic unless it specifically puts just one. Just like one oxygen. So 11.2 grams of oxygen. So the molar mass of oxygen is 16. 16 times 2 is 32 grams of oxygen. And 1 mole. Right. Grams cancel out. So 11.2 divided by 32. Now remember, when I do this cross off, I don't cross off the number. It just shows that the units cancel out. So 0.35. Could even, oh no, 2, right. 0.35 moles of oxygen. So yeah, this is to test your ability to notice that some elements are diatomic, and when I don't specifically put like one oxygen, you need to assume that we're talking about two oxygens because it's diatomic. Okay, let's deal with a different kind of conversion. So we are given 5 grams of water. We got to convert that to molecules. Okay, so this is a little different from what we've been working with. So first off, water is H2O, 2 hydrogens, 1 oxygen. That's what we're working with. So let's write that down here. 5 grams H2O. Okay. So if we remember Avogadro's number, 6.022 times 10 to the 23rd molecules, 1 mole. Remember what the mole was. A mole is this much of anything. Like a dozen is 12, a couple is 2. A mole is that quantity. In chemistry, we apply this to molecules. A mole of something contains that many molecules. So if we want to find out how many molecules, how many actual water molecules are inside 5 grams, we could use this conversion. So first off, we gotta convert this to moles. Gotta convert 5 grams of water into moles. Okay, we gotta find the molecular mass of water, like we did with CO2. So 1 hydrogen is 1.008 grams per mole, and oxygen is 16 grams per mole. Alright, so 2 times 1.008 plus 16.00, 18.2. And because water is such a common compound, most people have 18.02 by memory for the molar mass of water. 18.02 grams of water is in 1 mole of water. Okay, grams cancel out. Okay, so now we got to convert moles to molecule. Well, 1 mole of anything is going to be Avogadro's number. Molecules. Now remember, this is in scientific notation. Times 10 to a power. That's scientific notation. It's has a lot of zeros, but I'm just not going to write it that big. So 1 mole of anything is this much. We're talking about chemistry, and usually this number applies to molecules. And in fact, that's what we're looking for. So moles cancel out, and we're left with molecules. So now we could plug in everything. 5 times 6.022 times 10 to the 23. That divided by 18.02. We are left with 1.67 times 10 to the 23 molecules of water. Actual water molecules. So what's amazing about this is that, you know, we look at, say, a water bottle, and, you know, it's just mind-blowing to think that we could calculate how many actual water molecules are in there. So theoretically, if you want to figure that out, you could just weigh it, assuming that it's pure water. You just take its mass and easily find how many molecules of water are in there. So yeah, that's the power of knowing how to work with moles. So yeah, thanks for watching. I'm gonna have practice problems, a lot of grams to moles conversions, and maybe one tricky one. Definitely one diatomic problem. And yeah, thanks for watching, and I'll see you in the next video.